Hey guys, welcome back to Data Every Day. Today we will be looking at chocolate bar ratings and trying to predict an expert rating for the bar based on a variety of features about each chocolate bar. So this is very similar to the one I did yesterday on wine reviews, but let's get into it. So I'll start with these typical libraries, import them, and we can go get the file path to our CSV file over there. And we'll use pandas read CSV to give us the data. Okay, and we'll store that in data. So just take a look at it now. Okay, so we only have 9 columns, but there are very few numerical columns. A cocoa percent is a numerical column. The column we're trying to predict, the rating, is a numerical column as well. But the if we look at this, the date and this ref, if we look back here, ref is a value linked to when the review was entered in the database. Higher equals more recent. And so this isn't really going to give us any information. And just to show you that, I mean, let's get Seaborn in here so that we can create a heat map of the correlations just between the numerical features. So how do I do this? Oh yeah. So we'll start by specifying the figure size of our plot, which I think 12 by 10 works well. And then we'll do Seaborn's heat map, and we'll pass in the correlation matrix of the data frame. And then plot.show. And here it is. Okay, let me turn annotations on so it's easier to see. Alright. Looks like review date and the recency are almost almost have a correlation of 1.99. Obviously, because they're both go hand in hand. They're basically the same feature. But we can see it has almost no correlation on the rating. So I think these guys, ref and review date, are actually not providing us any useful information to the dataset. So I think we would be safe to just drop those columns, which will leave us with a measly 7 columns. Even 6 if you don't count the feature the target column. So data.drop, and what are they? Ref and review date. Okay. Whoops. And we'll just specify the axis and say in place. Okay. Now if we take another look at data, we can see these guys are gone. Now we have a proper data set of 7 columns. Now, I guess before we go any further, we should consider what are we trying to do. We want to pre-process this data set. So let me just write pre-processing. We want to we'll check for null values, remove any missing values, or impute the values with either the mean if it's a numerical column, or we'll do it on a case-by-case basis. Then we're going to check. Okay, you know, this is such a simple data set. Let me just write it out. So we'll check for null values first. This will get the matrix of of true and false values for if it'll be true if it's null, and this will sum across all the columns, so we get the counts of every null value in each column. And we can see only 2 null values. This could be the same actually, but basically, because this is so small, the best thing to do, I think, is just drop the row, right? Because the row that contains this, we still have nearly 1,800 examples. Dropping 2 rows off our data set isn't going to really affect the performance so much. So we can go ahead and do that. And a very simple way to do that is, well, data.dropNA just removes all the values and the row axis. And if you look at that, now we would have one with 1793 rows as opposed to 1795, because both rows were dropped. If we specified this to be 1, it would drop the columns that have null values. But we want rows, so we'll keep that. And we'll just rewrite data in that form. Okay, so now if we looked at the null values, there should be no more null values. Okay, next let's look at the data types. And as we can see, alright, so even though this is really a numerical value, it's being stored as a string. You can see cocoa% is an object or a string. And so we're gonna before we do anything to the other values, let's just turn this into a float. So we can do that. We'll just write a little function called remove %. Take in some data, and we'll just return that same data, but we'll apply element-wise apply a lambda function to it, which will for each element x will return that same x, but with the % stripped off, then turned into a float, and then divided by 100. And that will, you can imagine, take off the %, turn into a number, and then divide by 100 to get a percentage value between 0 and 1. And define that, and then we'll just call that remove % on just this one column here, cocoa%. You know, right before I do this, I actually want to rewrite these column names. You can see they're really sort of sloppy. They have a new line character in the middle of them, and I don't know, I feel like they're excessively wordy, especially here. So what we'll do is we'll just rewrite them. The way to do that, data.columns, take a look at it. This is the list of columns. We're just going to rewrite it as a new list. Company, specific origin, and the order is retained here. And cocoa %, location. This will just make it a lot easier to index it and reference different columns. Rating, and bean type, and last one is broad origin. Okay, run that. Now if we were to look at our data again, you can see everything has a very nice name. Okay, so now we will apply this remove % to the cocoa % column. And that will look like this. All the percentage values have been converted into numerical values. So we'll say cocoa % equals. Okay. Don't worry about that. The effect has been achieved. Alright, so now the last thing to do. We have to somehow find a way to turn these text values into numerical values. So one-hot encoding is what comes to mind. However, this will be a very high cardinality dataset after we perform one-hot encoding, because if we look at, for example, I think let's do specific origin. Okay, if we check out all the unique values in the specific origin column. Okay, yeah, how many in there? The length of this. There's 1,038 specific origins. So with one-hot encoding, this would add 1,038 new features to our dataset. And that'll be okay, but I think we're going to have to use a pretty high variance model to account for that. So a neural network will be best in this situation. So let's go ahead and convert all the categorical variables, all the categorical features, into one-hot encoded forms. So we can do this. First, let's make a list called categorical features. And this will just be the names of the columns with the categorical features. So it'll be everything except cocoa percent and rating. So I can just grab this and then remove cocoa percent and rating. Okay. So this is a list of our categorical features. And we're going to write a new function that will one-hot encode our whole dataset given a list of columns. So this is a useful function to use. You're free to take it for your own use if you wish. One-hot encode, call it whatever you like. We'll feed in a dataset and the columns that we wish to one-hot encode. And then for each column, in columns, we will get the dummies data frame, which will just be pd.getDummies of data subcolumn. So if you don't know what the getDummies method does, pd.getDummies, let's say I use this on company. Basically, there are 416 unique values in company, and it turns each one of those unique values into a column, and then the value of each example then becomes a 1 in the corresponding column and a 0 in all the others. So this is why it's called one-hot encoding, because there's one hot and all the rest are not. So what we're going to do is we're going to get a dummies matrix for each column in the specified columns, and then we're going to concatenate with the pd.concat the original data with the dummies. So we're going to take our original data set, get the dummies for a single column, concatenate it right on, and we'll have to specify the axis as 1 so that it goes side by side. And then we're going to drop the original column. Alright, so this is going to do it for each one of these. It's going to get the dummies for that column, concatenate it on to the original dataset, and then drop the original column without the dummy values off the dataset. And then we'll return data. So if we run that, and then we take a look at what that does. If we want to one-hot encode our data, and let's say we want to specify a single column. No, actually, we'll just give one column, which will be company. Well, what happened? Maybe because of the list. Yeah, alright. So the original company column, right, this guy, is gone, but it's been replaced with a dummies matrix for every unique value of the original company column. For example, here the company was A. Morin for example 0. So here for example 0, A. Morin has a 1 and all the others have 0. So what we'll do is, instead of just doing it for company, we'll do it for the whole categorical features list. And that will be, you can see the only remaining variables we have is cocoa percent and rating, because those weren't categorical, and everything else has been converted to dummy values. However, you see now we have 1,600 features. So this is why we're going to use a neural network. We'll use TensorFlow. And this is also a regression problem, since we're trying to predict a value between 0 and 5 as the rating, right? So first of all, let's split our data between y and x. So y will just be the rating column, and x will be everything except it. So now we look at x, it looks like this. Oh, what happened here? Oh, we never actually assigned this to data. Okay. So data will become the one-hot encoded version of itself. Alright, now we do this, now we do this. Okay, now this is our x, everything except the rating. And we're just going to scale it down using the min-max scaler. So let's go ahead and import that up here. So from sklearn.preprocessing, import min-max scaler. And this will fit this guy, the cocoa percent, also between 0 and 1, just to make it a little easier for our model to handle. So scalar equals min-max scalar, and then x is going to equal scalar.fitTransform x. So we'll fit the scalar to our x. It'll find the min and max of each column, and then it will transform x by squashing the min and max down to be between 0 and 1. So the whole range of every feature will be between 0 and 1. And that's already the case for all the dummies columns, so it will just affect the cocoa percent. And we'll just turn this back into a data frame afterwards, because the transform function returns a NumPy array. We'll keep the columns as they are. Done that. Taking a look at x now, and you can see everything has been converted to floats. That's okay. But this guy is now between 0 and 1. Right. Alright. Wait, was it already between 0 and 1? It was. There's absolutely no reason to do this, right? Was there? Oh, unless... no, there was, because it may not have gone up to 100% cocoa, right? Or 0% cocoa. So it'll stretch it out a little, actually. Okay. So now we will train our model. I think we're ready. This is a good x. We got a good y. So our labels. Well, really the target that we're trying to predict. And we can start training our model. First we'll set it up. And even before we do that, we'll just split our data, xtrain, xtest, ytrain, ytest. We'll have to use the train test split function, so let's go ahead and import that as well. And let's also import TensorFlow. Okay. So we'll run this. Ooh, what's wrong? Oh, I didn't pass in the arguments. X, Y, and we'll say train size of 80%. Wow, that was not... Alright. Now we'll start building our model. We'll use the functional API for Keras models. So we'll specify the inputs layer as tf.keras.input. And we'll say the shape is going to be a vector of 1655 columns, features. Then our next, we'll have two hidden layers. One with, they'll both be fully connected dense layers. And 16 nodes on each. I was doing some experimenting earlier, and it looks like this is a pretty good architecture. So here we'll pass in the inputs. Whoops. And here we'll pass in x. And then for the outputs, we'll have tf.keras.layers.dense. Only one value it will return because this is regression. And we will not give it an activation function because we just want the final predicted value. not transformed in any way. And x, and then model equals tf.keras.model. Specify the inputs and the outputs. And that, then we'll compile our model. So we will say our optimizer, let's actually specify the optimizer right here. Optimizer is going to be RMS prop, tf.keras.optimizers.RMS prop, and we'll give it a learning rate of 0.001. And then our optimizer will just be optimizer, and our loss will be MSE, mean squared error. We don't need metrics here because the best metric in this case will be the mean squared error, so our loss will just serve as our metric. And we'll compile it. And now let's just take a quick look at what our model looks like, model.summary. Even though it's a very simple model, it is 4 layers, 1 input layer, 2 hidden layers, and an output layer. And you can see the number of features, nodes in each one. And so it starts with 1600 features and returns 1 value as the prediction. And we will now train our model. So we'll specify the epochs as 50, just a starting value, and we'll store our model's performance in the history variable, and we'll say model.fit. And we'll give it xtrain and ytrain. And we'll give it a validation split, 20%. And our epochs will be epochs. And we'll give it a batch size of 32. Let's just make a batch size here. Okay. And then we'll just turn on verbose mode. Okay. Let's train it. See how that goes. That shouldn't take too long because it's pretty simple, just tabular data. Okay, it's already done. So let's plot how that looks. So remember that we stored history as our model's performance. So this is a history object, and it has an attribute called history, which would be a dictionary of all the metrics that we have. In this case, the only metrics will be loss and validation loss, because we didn't specify any more, and that will be the mean squared error. So that's a good way of understanding how our model is performing. We're going to plot our, like for example, if I index this at loss, this is the loss at each epoch of training. So you can see it goes down naturally. But what we can do is we'll plot this in right here. We'll write, let's make a new figure size of 14 by 10, and we're going to plot 2 curves, the training loss and the validation loss. So on the x, we'll have a range of the number of epochs. So it will okay. So we'll plot across the epochs on the x, and then for our y, we will plot the history.history loss, so the loss values, and we'll color the training loss as blue. We'll do the same thing, except here we'll use the validation loss and we'll color it as red. Then we'll just specify the labels. Okay, and actually I want to get the alright, this should be fine. Alright, and we can see pretty good. Our both curves decrease, and we can see there's probably here a minimum value of validation loss before it starts to go up again. So we're going to find which that is using numpy.argmin. Validation loss. So this will find the epoch that gives the lowest validation loss. And it looks like 10. So right here is the best model performance. So what we'll do is we'll go back up and change our epochs to 10, and we will reconstruct and retrain our model with 10 epochs. Now if we look at this, it goes down, and this should be the lowest value we can get. And finally, we will evaluate our model on the test set and see we get a lowest mean squared error of 0.29. So that looks really good. This looks like the best we can get. We could do some more experimenting if we wanted to see if we can get a better result, but this looks pretty good. So we took a very small data set with only 9 columns, cut out a bunch, got it down to like 7 or 6 columns, and then used one hot encoding to bring it all the way up to this many. And it looks like we did all right. So thanks so much for watching. Again, if you liked the video, make sure to hit the subscribe button and the bell, and leave a comment below with any suggestions for future videos or for the channel in any way. Thank you so much. I'll see you guys tomorrow.